Okay, you watched that video. What he had in each of those tubes was hydrogen peroxide, H2O2. And if you looked closely at this stuff, you'd see a bubble here and there. And then he dropped in that solid. It's a dark, blackish, shiny material, manganese 4 oxide. Dropped that in. And when he poured that powder stuff in, it went crazy. The rate went up by 1,000 or something like that, right? So no catalyst, H2O2, slowly decomposes into oxygen and water. But you put in catalyst and it went crazy. Well, a couple things we need to note about catalyst. Catalysts increase the reaction rate. In less fancy terms, they just speed up the reaction. Now, they don't get used up. At the end of that, you can see there's that powdered material sitting there at the bottom of the test tube. So they do not get consumed. Do not, maybe I should say are not consumed. The catalyst is there at the beginning, it's there at the end. They're not reactants, and catalysts are not products. That's why we write them up there. We say, well, it's not a reactant, it's not a product. And by the way, this reaction will happen on its own, but if we put a catalyst in there, it happens much faster. Okay, now let's tie everything together with no math and some cool little pictures that are going to tell us a whole lot. So I'm going to look at page 7.15, and I have enough room there? Okay. Here's what I'm going to do. Actually, I'm going to zoom that up a bit. There's my reaction. Nitrogen monoxide making N2 and O2. I'm going to draw this graph here. I'm going to go bigger. Okay. I'm going to do this. I'm going to draw a vertical axis, and this is basically G or H. Gibbs free energy or enthalpy. Going up, down. At the bottom here, I'm going to draw this. And I'm going to say reaction progress. That might sound kind of funny, but I can say, well, think of it as over here I've got reactants. And over time, eventually, I've got products. So like I've got reactants here. I'm going to look at the energy of the reactants as the reaction changes. And then finally products, what is the energy? Well, if I could sort of magically measure the enthalpy or the free energy of my reactants, NO plus NO. I have some kind of machine and it measures it. So I put the reactants in there, hit a button, and it does that. As soon as I drop, I'm getting ahead of myself. If I could check 10 minutes later or something, what I'd find is, here's the energy of my products. Here's my N2 and O2. Now that alone, that's what we've been looking at. It says, oh, this was higher in energy. There was more enthalpy or Gibbs free energy, and there's less. So I can say, oh, that's a negative delta G or a negative delta H. I can see, oh, this thing went down. It's exothermic or exergonic. And I can tell because there's my reactants and my products are lower. Now, in between what happens is, so over here I have these guys. There's their energy. When the reaction's over, I've got those guys. Now, in between, what I'm trying to do is say, okay, I want you two to react. So here they are, sitting there like that. As I push them together, they repel, right? There's electrons on the outside. So what I've got to do is they're minding their own business, this energy. As I push them together, they're like a spring. I'm compressing this thing. As I do that, the energy goes up. So as I compress those reactants, if I were sort of measuring their energy, what I would find is they would go up and sort of crest there. And at that point, what I would see is I've got nitrogen, oxygen, nitrogen, oxygen. There's that molecule and that molecule. And there's some kind of double bond in there. And what's happening is that double bond is starting to break. And that double bond is starting to break. And what I'm getting here is that bond is starting to form. And this bond is starting to form. So it's at the peak, like the old bonds are breaking, the new bonds are forming, and that's the sort of peak amount of energy. And after that, those bonds will continue to break, the new bonds will form, and if I was measuring the energy, what I'd see is it would come on down. Now this picture tells me a whole lot about what's going on here. There's my reactant energy, my product energy. I know it's exothermic or exergonic. I can see that I have this energy that I have to put into this reaction to get it started. It's like maybe putting a match to it and saying, okay, I got to get it up to that much energy before it will continue. Well, we have a name for this. That is the energy of activation right there. That's the amount of energy it takes to get a reaction started. Now, we're going to think of it as a speed bump. So we can say, oh, if it's a really big speed bump, we can make some guesses about how fast the reaction is going to happen. Big speed bump, slow reaction. Small speed bump, fast reaction. And these are completely independent. This means a reaction is spontaneous or favorable. It wants to happen. This in between tells me how fast it's going to happen. And we can draw a bunch of pictures on page 7.16. Let's look at these two. So it says exergonic. So there are my same axes. Same axes. It says exergonic. So I might think, well, here are my reactants. There are my products. The energy of the reactants, energy of the products. This says exergonic. So I'm going to say, okay, well, there's my reactants. There's my products. Now, this says the reaction is slow. So I can think whatever happens in between looks like that. Now this reaction says it's fast. So the change in energy is the same, but my speed bump looks like that. The change in energy is the same for both, but slow, fast. And I can go the other way. I can say, okay, it says endergonic. Here's my reactants. There's my products. It says it's slow. So I think, well, if I were to make this happen, there's a big speed bump in between. Similar, reactants, products, but if I do force this thing to happen, not a very big bump. So, favorable, exergonic, exergonic, endergonic, endergonic. Slow, slow, fast, fast. Sounds like some kind of dance lessons. Okay. So that's everything we've done. Sort of, is it exothermic, endothermic? Is it exergonic, exogonic? I don't know. Anyway, you know. And is it slow or is it fast? All right. Let's do one more thing. Page 7.17 then gives us a chance to think about So here's my spontaneous reaction. Here's my reactants. Here's my products. Lower in energy. Now, it says it's slow. So I have some big speed bump. Meaning, yeah, this wants to happen. It's just not going to happen very fast. Now down here, I've added a catalyst. So everything is identical. Reactant, product. And I can think, oh yeah, the old reaction. Now with a catalyst, it's going to look something different. It might be as simple as this. Or it might have a couple of different weird humps, but like that. But the point is, the energy of activation, E sub A, is much, much lower than it was without the catalyst. And so now we can do everything we've done in this entire chapter with no math, but with these silly little pictures. Let's do a couple of examples. Page 7.18. It says, and I'll zoom in for improved readability here. It says, iron and oxygen form rust. That happens. You leave iron, oxygen, some other things. It will rust for sure. But is it rapid? No. It might take days or weeks or years or something. So it says, well then, what does the activation energy and the delta G look like for this? Well, we could draw our same picture. There's G. Here's reaction progress. And I said, well, iron and O2, their energy's up there. If I was put some kind of machine and measured their energy, and rust is down there. Like, I know, yeah, this is going to go there. Eventually, remember, nature's lazy. Nature's going to go from iron and oxygen to rust. But it isn't going to happen very fast. So there's my energy of activation. There's my E sub A. And here is my negative delta G. One last thing. Now it says, here's my delta G for this reaction, minus 16. But at room temperature, it doesn't really happen. Well, remember, that means if we know that if we heated it up, it would go much faster. But at room temperature, it's very, very slow. So I could say, okay, G, reaction progress, here's my H2 and N2, and it says minus 16 kilojoules per mole. So I know that's the difference there. And it says it doesn't happen at room temperature. Well, it means it's really slow. So that just means in between, there's a big E sub A. That's to the peak there. There's my delta G, there's my E sub A. Students usually find this to be pretty easy. There's really no math here. It's really just sort of drawing these pictures of everything we've done. All right, that's going to sort of wrap up this entropy, enthalpy, and rates of reaction part of Chapter 7. So we're going to stop here and then change gears and do something completely different in the next part of Chapter 7. All right, I'll see you then.